Hello, and welcome to the first video of quantum mechanics. Now, quantum mechanics is unlike any other subject in physics, whereas we don't fully understand the phenomena of quantum mechanics. So, unlike, say, thermodynamics, where we understand where a lot of the energy is going and transferring between, in quantum mechanics, we don't understand the underlying principles of what makes these things happen. So since we don't really fully understand quantum mechanics too well, there's lots of different interpretations of it and a lot of philosophical debate between like what interpretation's better, what different interpretations mean for the universe, and a lot of it is up for debate still today. If you're interested in learning more of the philosophical interpretation of quantum mechanics, I recommend some other YouTube channels like Sean Carroll's videos. He goes in depth a lot about his interpretations of quantum mechanics and different ones and everything in the universe, basically. But for now, I'm just going to go over some of the underlying mathematical principles that lead to quantum mechanics and applications of quantum mechanics. And so the first thing that anyone learns in quantum mechanics is called the Schrödinger Equation, and it is I h bar partial derivative of psi with respect to time equals minus h bar squared divided by 2m partial derivative squared of psi with respect to position this time plus v times psi. So this right here is the Schrödinger equation. It's the basis for all of quantum mechanics, how we solve all quantum mechanic problems. And basically what it says is for any psi wave function, that means any psi wave function has to be a solution to this differential equation. So, and the way we find these wave functions is by solving for different potentials of V. V is our potential energy of the system so far. If you've taken any Hamiltonian mechanics, this is pretty similar to Hamiltonian mechanics, where the Hamiltonian is equal to the kinetic plus potential energy. So we'll see this come up later too when we dive even deeper into the equation. The next thing I want to talk to you about is this new constant, h bar. And I'm using h bar here because it's more convenient than writing the original Planck constant is what it's called, which is the Planck constant divided by 2 pi. Now this Planck constant is pretty familiar because it relates energy and momentum. I'll go over that a little later in the chapter. We'll dive deep into it. But for now, just know that this h bar is a constant, and it is 1.05473 times 10 to the minus 34. And these are pretty interesting units as well, joule seconds. These units are actually very important for what this constant means, so I'll come back to that also later. For now, I'm just going over like the Schrödinger equation in general, and basically how this all works is, so this is a constant, this imaginary number I times this constant, the derivative of your wave function with respect to time equals this big constant, h bar squared over 2m. M is the mass of whatever particle you're looking at. The partial derivative squared of psi with respect to position squared this time, plus the potential energy times psi, your wave function. And for any psi that is the solution of this, that is like a solution to your system in quantum mechanics. And so for the first few videos, all we're going to be doing is solving new potentials for this differential equation and coming up with new solutions to different potentials. And then later we will build on that to show what these different potentials actually mean, what they can be used for in real-world applications. Okay, so the next thing is that quantum mechanics is inherently statistical. And what I mean by that is that quantum mechanics is not a definite science. Well, it's a definite science, but we can't definitely predict the science. So what we mean by that is, say you have a normal distribution. You have a normal distribution like that. Your most probable value is, let's say, x here. Now, this is your most probable value right here, but if you actually run whatever experiment this is, you can get this value, 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 all with different probabilities. Now, all quantum mechanics is taking this statistical idea and applying it to your wave function, psi. So psi is actually what's called a probability distribution. So basically, this psi right here could be this probability distribution right here, as long as it's able to solve the Schrödinger equation. So if this is an actual solution to the Schrödinger equation, then this probability distribution is the solution to some potential for this. So what that means is that quantum mechanics is inherently statistical. Now, about these probability distributions, one thing we know that always has to be true for a probability distribution is that the sum of all probabilities has to equal 1, from 0 to infinity. That probability always has to be 1. You can never have less than 1 probability, because that just means the probability of ever finding this is less than 1. So another way of thinking of that is taking this distribution and like adding the probability here, adding the probability here, adding the probability here, probability here, and basically just taking all this and setting it equal to 1. So you can easily say that that is the integral of psi, and the limits are going to be from negative infinity to infinity. And let's just say our axis here is x, and this axis is probability dx. Now that works pretty well until our psi function becomes more complex, because look, we're allowed to have complex solutions here inside of the Schrödinger equation. And complex numbers don't behave pretty well with this integration right here. So instead, we have to do something else. Instead, what we have to do is take the modulus of psi and square it. Now this has to equal 1. And this is one of the most important underlying principles of quantum mechanics right here. This fact right here. Now, since psi is a probability distribution, what could modulus squared of psi be? Well, really, what this is a probability density. So it makes sense, since if this is a probability density, we can integrate that over this all space right now, and that gives us the total probability, which has to be 1. But let's say I just want to find the probability from like here, let's call this point A, this point B. Then that's pretty simple. We just do the integral from A to B of the same thing, psi squared x, modulus of psi squared dx, as long as psi is a function of x. We can see psi's of multiple variables soon later as well, but for now we're just working with psi equals psi of x. Okay, and so that's going to be it for this first video. I just wanted to make sure to go over the statistical point of view of quantum mechanics, the underlying statistics that we'll need for this, as well as an introduction to the Schrödinger equation, which we'll be having a much more deeper discussion of its implementations later. Thank you.